Hello, everyone. My name is Burkhard Müllitzer. It's my great pleasure to introduce Kyla de Villa, who will give today's CMEC talk. And Kyla is a second-year graduate student in our Department of Earth and Planetary Science at UC Berkeley. She works in my group and does ab initio simulations. She has a background in chemistry, and background is appropriate because in the background you see her degrees. Um, Also, if you want to meet Kyla in person, you can actually attend the Gordon Conference this summer. She'll have more results to share, and you can talk to her about future projects that may actually involve ice giants. So ice giants have not been visited a whole lot by spacecraft, and there's a new mission being planned that will go to Uranus and will be orbiting it, and probably there will be an entry probe. And that is very important that young people are involved in this mission, in the preparation, and understand why is the mission flown, why are we so interested in these planets, because the current plan is that the spacecraft will arrive there in 2045 or maybe in 2050. And when people like me think about how old we are at that moment, you think like there should be some younger people involved, because we will definitely be retired, assuming we're still active and alive at that moment. So Kyla has a unique angle to this properties of ices. She is applying ab initio computer simulations and studies them in various aspects. And once in a while, when you run these simulations, you discover something completely new, something that nobody's ever seen before. And that happened to Kyla. She discovered a new state of matter, which we now call double superionicity, and she will explain to you what it is. And other people were equally excited about this finding, that the paper was actually published in Nature Communications. So it's a great success. Her first paper was published in that high-profile journal, and today Kyla will tell you about it. So thank you very much for listening, and questions later.
Great. Thank you, Burkhard, for the introduction. Yes, as Burkhard mentioned, I'm a PhD student at Berkeley, and it's exciting today to be able to tell you about all the work that I've been doing related to ice giant interiors, that is Uranus and Neptune, and then also related to the formation of their really strange magnetic fields. So my work primarily focuses on doing atomistic simulations like you see here on the right, but lately I've been getting into magnetohydrodynamic or MHD simulations on these planets. Sorry. So as Burkhard mentioned, the study of Uranus and Neptune is actually fairly modern and not nearly so developed as for the other planets in our solar system. And I would say was really jump-started by the Voyager 2 mission in the 1980s. So through the 70s and 80s, there was this really interesting and rare planetary alignment happening of all of the giant planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, that only happens roughly every 175 years. And so this would allow a single spacecraft to be able to use gravity assists to visit all four spacecraft, or I should say all giant planets, with only one spacecraft, obviously allowing a lot of novel observations to be made with really reduced cost compared to sending 4 individual spacecraft. So Voyager 1 was sent to Jupiter and Saturn and then was optimized for a flyby of Saturn's moon Titan. And then Voyager 2 actually completed the grand tour, visiting all 4 giant planets, with Uranus in 1986 and Neptune in 1989. And so Voyager 2 was the first, and to this day is still the only spacecraft to visit Uranus and Neptune. And it only passed by each of these planets for between 16 and 36 hours. And while doing so, it measured their gravitational fields, rotation rates, luminosities, atmospheric compositions, magnetic field morphologies, and lots more. And it also took these really famous pictures. However, if you've been following space science news lately, it's been suggested that Neptune is not actually this lovely sapphire color. Researchers at Oxford recently reprocessed the Voyager 2 camera data and have decided that this is a more accurate true color picture of Neptune. And so before I get too deep into this talk, I think I should address the misnomer that is ice giant, as this is how these planets are referred to. So clearly near the sun, it's quite hot. And as you get farther from the sun, the ambient temperature of the solar system decreases. and past a certain point, which is called the frost line, water freezes. And further out, we get frost lines for ammonia, methane, carbon dioxide, SH2. And so Uranus and Neptune exist past these points and likely formed past these points, meaning that as they grew, they were able to accrete not just rocky bits, rocky planetesimals like the inner planets, but were also able to accrete large amounts of ice. However, now these planets are super high temperature, super high pressure. We just call them ice giants based on their composition, not because they're characterized by being cold solids. So before Voyager 2, the interior modeling of these planets had very few constraints because very little was actually known. So you could abstract planets to be perfectly spherical, and then by estimating the mass and radius, you could estimate the planet's bulk density, and then you could build a toy model that matched intuitions for composition and structure. So this model I'm showing on the right is from 4 years before Voyager 2 arrived to Uranus, and is a really traditional, to this day, 3-layer model of these planets, characterized by a rocky, iron-rich interior, a hydrogen, helium, methane-rich atmosphere. Methane is what gives these planets their blue color. And then on the interior, a water, methane, ammonia, what we call planetary ice mantle. But the hope was that data from Voyager 2 would lead to a lot less ambiguity and guesswork related to the interior structures of these planets. And unfortunately, that really was not the case. So I thought I could walk you through some of the measurements Voyager 2 made at Uranus and Neptune to demonstrate this. So for example, Voyager measured the luminosity of each planet, which really can be used to understand how much heat the planet is giving off, particularly relative to how much heat it's receiving from the sun. So as we see on the right, Neptune gives off more heat than it receives from the sun, which is expected for a planet that's cooling and has an adiabatic temperature profile. However, Uranus was measured to have no intrinsic flux. It was only emitting as much energy as it received from the sun. And so there were a number of suggestions for why this might be the case. Perhaps Uranus had a thermal boundary layer somewhere inside, preventing heat from escaping upwards and resulting in a very hot interior. Another suggestion was that Uranus experienced a giant impact at some point in its history, which caused some sort of interior restructuring and redistribution of heat. However, I would say to this day, there's no accepted explanation for why this is the case or why these planets differ in this regard. And so I would argue that the ambiguity here really arises from the fact that we know so little about the thermal properties of the materials that these planets are made of. So in this case, planetary ices. Another explanation I've heard recently from someone also at Berkeley who studies atmospheres of giant planets is that perhaps Uranus only emits heat from the atmosphere intermittently, and Voyager just missed this happening. But even this possibility, I would say, speaks to the need for us to get better spacecraft data, because if this is the case, then we clearly have a really poor understanding of these planets' atmospheric cycles. But going back to planetary ices, we really need to study these more to be able to understand these planets' luminosities. Because, for example, if there was a thermal boundary layer, we would have to study the ices sufficiently to know if this was even, like if there was even a planetary ice material which could potentially serve as a thermal boundary layer. So Voyager also measured Uranus and Neptune's gravity fields, which are represented numerically using spherical harmonic coefficients, which really define the magnitude of how much the planet's shape differs from a perfect sphere. So for example, here on the left, I'm showing the J2 perturbation, which is really how much a planet is bulging about the equator, which happens due to the planet's rapidly rotating. I'm also showing J4 here. And of course, these values have also been measured over time for Jupiter and Saturn. So here you'll see old and new. New for Uranus and Neptune just means a reinterpretation of Voyager 2 data, versus new for Jupiter and Saturn actually means new spacecraft data. But really what's important to focus on here is that there's significant differences in the errors associated with these different planets' spherical harmonic coefficients. So we'll see that Uranus and Neptune, the errors on their J2 and J4 coefficients are something like 1 to 3 orders of magnitude higher than for Jupiter and Saturn, meaning that the gravitational field for these planets is known with much less precision. And while gravitational coefficients have been really invaluable in recent years, for constraining the interior structures of Jupiter and Saturn, those measured for Uranus and Neptune are not accurate enough to really resolve any ambiguities on their structure. These values can be matched using a great variety of different interior models. So here I'm showing really two end member models for the interiors of Uranus and Neptune. So on the left, we have our traditional ice giant model, which would have a rock to ice ratio of something like 1 to 20. And you can see here, because of the rock-rich interior, you get a really high density at the core. On the right, we have a kind of more popular modern interpretation, which was called the rock giant model, which is characterized by having a rock to ice ratio of more 1 to 1. And this is more popular, I'd say, gaining popularity in recent times due to other work that's been done, the first of which showing that Pluto and also the moons of Uranus and Neptune most likely have a rock to ice ratio closer to 1 to 1 or 1 to 2. And secondly, there's been a lot of work done showing the miscibility of rock and ice, like work done by my group mate Tanya, who I think you all know, or showing the miscibility of ice and the gaseous atmosphere, which really allows this much more smeared out density profile. And again, both of these models are matched by the gravitational coefficients that were measured. So as it turned out, it really was just the strange magnetic fields of these planets that have proven the most useful to constrain their interior structures. So I thought before I get into that, I could really briefly review what I mean by their magnetic fields and dynamos and how they're formed. So in a planetary context, a magnetic field is a region of space in which moving charged particles feel the effects of a magnetic force. And then so a dynamo, or for planets, we would call this a geodynamo, is a process by which a planetary magnetic field is generated and then self-sustained by fluid motion in the planet. So this requires three things. The planet has to be rotating at a sufficient speed. You need electrically conductive fluid, and you also need convection. And so we can see on this figure on the right, rotation and convection together lead to these really highly organized rotating columns of conducting fluid, which are great for generating these magnetic fields. So through the early 1980s, pre-Voyager 2, all planetary bodies that had been observed to have magnetic fields had these dipolar, relatively axisymmetric magnetic fields like I'm showing here. And so these fields are known to be generated by convection deep inside planets. So for Earth and Mercury, that would be their liquid iron outer cores. And for Jupiter and Saturn, that would be convection of metallic hydrogen deep within the planets. So you can imagine everyone's surprise when Voyager 2 passed by Uranus and observed this. The magnetic field is highly asymmetric with strong quadrupolar and octopolar elements, as well as dipolar. And of course, this sparked a number of hypotheses of why such a strange magnetic field would be observed. Perhaps a geomagnetic reversal was being seen, but if this happens on the same frequency as Earth, this was maybe a 1% chance of Voyager observing this. Perhaps Uranus's large obliquity was somehow influencing the magnetic field. Uranus basically rotates on its side, and then also could a giant impact again have somehow changed the convection processes within the planet? So there was no accepted theory, but it was still expected that Neptune would have a normal dipolar field when Voyager 2 passed by 3 years later. However, clearly this expectation was not met. Both planets have strong quadrupolar and octopolar elements, and both planets have asymmetric or non-axisymmetric magnetic fields. And so here when I'm talking about dipolar, quadrupolar, octopolar, I mean that the magnetic field is being represented as a sum of these spherical harmonic contributions. However, spherical harmonic modes decay with distance, to like 1 over distance to the power of degree plus 2. So basically lower degree spherical harmonics like dipolar decay slower, which is why when magnetic fields are generated really deep inside planets like Earth or Jupiter, only the dipolar field is visible from the surface because all of the higher order spherical harmonics have attenuated by the time the field reaches the surface. And so the fact that for Uranus and Neptune, we can see these octopolar and quadrupolar elements, as well as the dipolar elements, suggested that these planets had material convecting close to the surface of the planet, meaning the magnetic field was being generated close to the surface, so that these higher order spherical harmonics could still be observed. They didn't have like this space to decay before reaching the surface of the planet. And so in 2004, Stanley, working with her advisor Bloxham, demonstrated that this convection morphology I just described could indeed replicate the observed magnetic fields of Uranus and Neptune. So they argued that this icy layer of these planets would have to be broken into two parts, with the top part being a conducting, convecting fluid, and the bottom part being most likely a stably stratified fluid. And so here the atmosphere is not shown, and we still have our rocky, iron-rich interior. But 20 years on, I would say that this work, while really foundational, has some caveats. The first of which being that they did not incorporate any depth dependence of really important material parameters like density, viscosity, conductivity, etc., into their simulations. They also provide really no material science-based context for this convection boundary. Oh, sorry, I was looking at the chat. Like there should be some material explanation for why you would have the upper part convecting and the bottom part not. Like, is it a phase boundary of the same material? Is there compositional stratification? So I would say 20 years on, there's still no accepted explanation for how this interior structure would develop. And I don't list this here, but thirdly, the computational capabilities we have evolved amazingly over the last 20 years. And so compared to modern simulations, their spatial and temporal resolution is very low to what we can achieve now. So I would say the state of the field is as such. 35 years after Voyager 2 visited these planets, there's still no interior model of the ice giants, which can match all of these important constraints simultaneously. And I would say that we need three things to better understand these planets' interior structures. The first, really the most fundamental, is more accurate spacecraft measurements of the gravity fields, the magnetic fields, luminosities, rotation rates, and we'll talk about this more later. Secondly, it's really imperative that we actually understand how the materials inside these planets behave at these extreme pressures and temperatures. And then finally, I would say we need dynamo models of these planets performed with modern computing power and using physically informed equations of state and transport properties plugged into them. And so this would either verify past results or indicate that our models need to evolve, either of which I think would be valuable. And so these last two I have been working on these latter two objectives. So I primarily focus on performing atomistic simulations. Density functional theory, particularly molecular dynamics, is my most common tool. And so in this method, electron density is calculated for a group of ions and is then used to compute the forces on the atoms that drive atomic motion. And DFT is a really excellent computational tool because it lets us study the behavior of matter at extreme conditions that are either totally inaccessible to laboratory settings or would be very, very expensive to achieve. So for example, this simulation I'm showing you of crystallization takes place at 6,000, or I should say 6 million atmospheres and 5,000 Kelvin. And DFT is also a really popular tool for this purpose, as it really reduces the dimensionality required of our calculations by calculating material properties as a functional of electron density, which is three-dimensional, as opposed to full electron wave functions. However, I would say DFT, for all its benefits, is still very limited in system size to hundreds of atoms and is really limited in time scales. So at most, the nanosecond time scale, really most people do like in the tens of picoseconds. So I've also been learning how to use machine learning simulations to be able to study these materials on much longer length and time scales. With the hope that by doing so, material properties that cannot be studied on really short length and time scales will emerge. And so this method works by kind of the following workflow. You do have to have DFT calculations to train the neural network on. So you generate DFT data for the systems, temperatures, and pressures that you're interested in studying. And then you would feed into a neural network the atomic coordinates, energies, and forces. And so once the neural network is properly fit, you only need to feed into it atomic coordinates, and it can predict the energies and forces and drive molecular dynamics with system sizes and simulation times many orders of magnitude higher than is possible with DFT, because the process is so much faster without having to explicitly calculate the electronic structure. So my first project focused on studying superionicity in what we call HCNO compounds. So compounds composed entirely of those elements, representative of mixtures of water, methane, and ammonia. So materials are superionic if they exhibit light nuclei, like protons, sodium, lithium, helium, diffusing like a liquid through a stable lattice of heavier nuclei. So here on the left, you can see that in gold and silver, we have sulfur and carbon, clearly maintaining their stable crystalline structure, although they're vibrating a bit. But the protons in the structure are now diffusing widely like a liquid. Water, ammonia, and ammonia hydrates have all been shown to exhibit superionic behavior across a really broad range of pressure and temperature space. So as an example here, I'm showing a phase diagram of water. And so this actually makes the superionic phase really interesting to the ice giant planets, because many models of Uranus and Neptune assume that these planets are enriched in water and ammonia, as well as methane. This phase diagram also shows proposed isotopes of Uranus and Neptune, which would imply that really deep within these planets, pure water should exist in a superionic state. And finally, superionic materials are interesting to the ice giant planets because they can be highly ionically conducting, often at pressures and temperatures where they're not electronically conducting, which may make them important for dynamo generation in these planets. And then going back to this model of Uranus and Neptune's convection, a popular theory is that this stably stratified layer here is due to this layer being superionic water and this layer being ionic liquid water. And I myself do not necessarily adhere to this point of view, but this very popular theory, I think, raises interest in studying superionic materials. So thus motivated, we used DFT-MD to study 13 hydrogen-bearing ices listed on the right, with pressures ranging from 50 to 500 GPa. And amazingly, we observed a superionic phase in all of these materials upon sufficient heating, which would imply that superionicity is either extremely common or, if not ubiquitous, in these materials at sufficient temperature and pressure. And we were also really interested to find that the diffusive properties of these materials are strongly correlated to their proton fractions. So our first observation was that the more proton-rich a material is, the lower temperature at which it becomes superionic, compared to really proton-depleted structures, which only become superionic at much higher temperatures. And this can, of course, be related to the local bonding environment of these materials. So when materials have fewer protons, or I should say when they have fewer heavy ions, they're proton enriched, like these yellow and green lines, that means each proton is surrounded by fewer heavy ions, as indicated by the sum of the heavy ions at a certain distance. And so this makes them less constrained and able to diffuse at a lower temperature. And diffusion, of course, is related to activation energy. And so we found the diffusivities of these systems were well modeled within the Arrhenius trend, with the log of the diffusivity being linear with 1/T. And so the cool part here is that the slopes give the activation energy. So we can see the materials which diffuse at a much higher temperature have a steeper slope, indicating a higher activation energy. And finally, we calculated the ionic conductivity for each of these materials. And really the important takeaway here is that all of these materials had an ionic conductivity within an order of magnitude above or below that of water and ammonia at high pressures and temperatures. And so water and ammonia are often used to model planets. So it's interesting to show that these materials are not unique for their high ionic conductivity. However, the focus of our work was our observation of what we are calling a novel doubly superionic phase in these materials, in which two elements will diffuse superionically simultaneously. So a typical high pressure ice, when heated, transitions from the solid phase to the superionic phase and then to a liquid. However, in roughly a third of the materials we studied, we observed a second superionic phase, in which following the superionic phase, a second ion type, either carbon or nitrogen, will start diffusing at the same time as the protons through a stable sublattice of the remaining heavier elements. So two popular ways to visualize data to determine if something is superionic are looking at mean square displacement plots and looking at trajectory plots. So the way you read mean square displacement plots is this is really an indication of how far on average ions have moved over time. And so for superionic materials, you would expect protons to be diffusing, whereas the MSDs for the heavier ions should be 0. And looking at trajectory plots, we can see here that nitrogen in blue and oxygen in red, while vibrating around their potential wells, are not diffusing, versus the protons, all of these white strings are tracking the trajectory of a proton, are diffusing really rapidly and widely throughout the cell. For the doubly superionic phase, now we see a second ion type is diffusing versus the oxygen here in red still has a 0 MSD. And again, here I've hidden the protons so you can see the nitrogen trajectory better. We can see that the nitrogens have started diffusing widely through the cell. Maybe a better visualization is a video. So here you can obviously see the protons diffusing wildly, and occasionally you'll see a nitrogen ion jumping. But if we remove the protons and speed up the video, you can see the nitrogen ions diffusing quite rapidly and throughout the entire cell as well. So we were obviously concerned with showing that this phase was energetically and structurally stable. So we performed a number of additional simulations using DFT in the NVT, NPT, and NPH ensembles. We also used large cell machine learning simulations, and finally two-phase DFT simulations. And all of these methods were in excellent agreement, which was really cool. And so to feature some of our cooler results, here's what the nitrogen diffusion looked like in a roughly 2,000 atom simulation. And again, here I've hidden the protons. And so the blue lines being traced again indicate the diffusion pathways of the nitrogen ions, which we see diffuse really rapidly through the entire cell. This one was probably my favorite. So this is a two-phase simulation. So what you're seeing happen is we had on one side a doubly superionic cell, and on the other side, a liquid cell. And we're able to show that the oxygen ions will crystallize out of the liquid, and the nitrogen ions and the protons will continue diffusing superionically. And so this was important to show that the doubly superionic phase was not just an overstabilized solid that should be melting, but was actually the energetically stable phase of the two at those conditions. And this is also something that's probably not very important, but I thought was very cool. If you produce superionic isosurfaces of these materials, so really these on the left show the areas in the cell that protons spend most of their time when they're superionic, which is really mostly circulating the oxygen ions. The nitrogen ions, for the most part, try avoiding the oxygen ions. But if you overlap their isosurfaces, you'll see that for the most part, these ions rarely cross paths. So their diffusion pathways are largely intertwining. So of course we found this result to be very cool, but I think the more important takeaway here is that our discovery of this phase emphasizes how little is known about planetary ices, and really how little is known about what's going on inside the interiors of ice giant planets. Related to the doubly superionic phase we found, I think that it could be important for ice giant interior processes. So for example, now that there's two diffusing ion types, there should be a heightened ionic conductivity. We also observed in all of these materials a pressure temperature, I should say a discontinuity in pressure upon this phase change, which within a planet would imply that there should be a density change in the stratification. And work on this is ongoing, but I also think that you would observe changes in other transport properties like viscosity upon this phase change. So more recently, I've been working on another project in a collaboration with Ava Zurich's group at the University of Buffalo, and we've been studying superionic diffusion in what we're calling dilute ammonium hydrides. So as you can see on the left, these materials are characterized by, at 0 Kelvin, having NH4 clusters, and then having protons of different symmetries kind of spread throughout the cell. So here in red, these are also protons. And so the Zurich group was interested in these materials for their superconducting properties, and I'll let you read Xiaoyu Wang's paper when it comes out later this year. But our interest here was studying the superionic properties of these materials because no one has studied superionic diffusion in such proton-rich materials before. And a number of really interesting trends have emerged. For example, the superionicity at such low temperatures is unique compared to what's been studied in this chemical space. Also, because these protons exist in different electronic environments, at the lowest temperatures, like here at 450 Kelvin, you'll see that some proton types are diffusing throughout the cell versus others are not diffusing. So for example, here I'm showing these chain protons. Here's the dark line, they're here in red, start diffusing at 450 Kelvin versus these white protons are only orbiting the nitrogen ions. And another interesting result we found was that protons will diffuse through different mechanisms depending on the temperature. So at really low temperatures, like the 500 to 1000 Kelvin range, diffusion is dominated by proton shuttling, which is really protons hopping between nitrogen ions to get through the cell. Whereas at higher temperatures, diffusion is primarily dominated by protons just hopping between potential wells without having to connect to a nitrogen ion for that to occur. But I would say there's still a huge amount of really foundational work that needs to be done to study planetary ices, to actually be able to understand processes on the interiors of ice giants. And so I'm hoping to focus on this work for the duration of my PhD. So foundational for dynamo generation in these planets is the electrical conductivity of these materials, both ionic and electronic. And to understand the thermal evolution and heat flows, excuse me, in these planets, we need to know their thermal conductivities of the constituent planetary ices. And then to be able to understand how solid, superionic, and liquid phases will flow and how this influences stratification and how this drives convection, we really need to calculate viscosity of these materials. And finally, by calculating equations of state that relate pressure, density, and temperature, we can determine what materials and what phases of these materials are actually possible to exist within these planets, given radial and given density and temperature radial dependent constraints. And so the second project I've been working on is running dynamo models, which you can plug in the equations of state and transport properties that you can calculate with the atomistic simulations as I've just described. And so by doing so, we can plug in these values, run dynamo models, and then assess how planetary profiles match up to measured magnetic field morphologies. So the input here would be a planetary structure. So you give a number of layers, the relative depth of each layer. So one example would be Sabine Stanley's model that I'm showing here. And then you would also have to give a temperature or entropy profile throughout the planet. And then really importantly is the depth-dependent material properties. So density, thermal conductivity, viscosity, conductivity, because all of these control the flow of charge, mass, and heat. And so once you have set up your input of the planetary structure, these are plugged into an MHD code. I use one called Rayleigh, and this code solves this series of coupled fluid dynamics equations. And so this code can provide so much information about what is happening inside a planet with the parameters you provide. But what we're really interested in for my project is the magnetic field. And so once these simulations have converged, they will output a magnetic field morphology at the surface, which can then be compared to observations. And so this allows us to then determine what interior structures, what compositions, temperatures, etc., could possibly match our observations of the magnetic field and really help us constrain what's happening inside the planets. So to wrap up, as Burkhard mentioned, following recommendations from the most recent planetary science decadal survey, it's very likely that the next NASA flagship mission will be to Uranus, sending both an orbiter and an atmospheric probe. And without a name, this mission is currently being nicknamed UOP. It will probably launch in about 10 years and hopefully arrive around 2050. And the spacecraft will definitely provide much better constraints on all of the observables that we've already discussed as being important. And so while this new data will be revolutionary for modeling these planets' interiors, they really have to be paired with highly accurate equations of state for their constituent materials in order to really determine the planet's composition and structures. So I'm hoping that my work over the next few years in this area can help fill that gap. So thank you all so much for your attention. I'm happy to take any questions.
Thank you, Kyla. Any questions? So since I would suggest if you have a question, you can raise your hand or just speak up if you like. And maybe you can stop sharing your screen, Kyla, and we can all see each other a little better. And maybe we can stop recording. That would also be good, Miriam.